Today we are going to look at the course objectives and mathematical preliminaries that we need for this course. Okay, so what we are going to do is to seek answers to fundamental questions about computing. In particular, we want to know what is computable and what is not computable. And after we answer that question, we then want to know what is tractable, computable problems and what is not. By tractable here means that after we know that a problem is computable, we want to know whether that problem can be computed efficiently. Okay, so that is tractability. So our approach is to devise computation models not restricted to any specific hardware device and study computing based on these models. In other words, we want to come up with abstract models. Okay, so that is the models we are going to study computability. In particular, this model should consist of a processing unit and with memory. Okay, so we don't worry about any specific details of these components. Okay, so we just so abstractly, we want to have a processing unit and a memory. Then we can look at several different devices based on the types of the memory we are going to have. So we are going to look at computing with small memory. Okay, so by small, it really means that it's for a particular problem, the memory is really fixed. Okay, so it's small. And we call this computing device a finite automaton. Sometimes we also call it a finite state machine. And then the next computing device we are going to study is called push-down automaton, or PDA, which is a processing unit plus a unbounded stack memory. And then after that, we're going to study a general computing device, which is called Turing machines. Okay, so that Turing machine is a processing unit with unbounded tape memory. So we are going to use Turing machine to study or to answer a general question: what is computable and what is not? And after that, we are going to look at resource-bounded computing, or asymptotic resource-bounded computing. So in particular, these resources we have are time and space. Okay, so we have, in particular, for efficiency, we want to have a polynomial time computable problems. And for space efficiency, we will either have polynomial space computable problems. Okay, and then we also want to know what problems cannot be computed efficiently in time or in space. Okay, so that is what we are going to learn, what we're going to learn in this course. So before we look at these computing devices and the problems these devices can compute or recognize, we need some preparations or review of relevant math concepts and how we manipulate math objects. So that means operations. And also we need to look at proof techniques. So in particular, we are going to look at sets and operations, Boolean variables and operations, sequences and tuples, functions, relations, graphs, strings and languages, and finally, proof techniques. Okay, so a set is simply a collection of elements. For instance, we can write A, which is a set of three numbers, 1, 2, and 3. Okay, and also we can look at a Cartesian product of A. So we use this cross to indicate this is a Cartesian product. So this is the elements. So 1 and 1, 1 and 2, 1 and 3, and then 2 and 1, 2 and 2, 2 and 3, 3 and 1, 3 and 2, and 3 and 3. So you have altogether, in this case, 3 squared, which is equal to 9 elements. And this is another example, C. So it has an empty set. So this is curly brackets, indicates it's an empty set. Okay, and 1 and 2 is a this is an element, which is also a set. And 2 and 3 is a set, which is a subset of A, and 1, 2, and 3. Okay, so in this set, all right, its elements, okay, in this set C, its elements are also sets. Okay, so these are subsets of A. Again, curly bracket without anything in it represents there isn't anything in that set. So we call it empty set. Okay, so this is empty. Oops. Let me erase this. This is empty set. So sometimes we use a 0 with a backslash, also with a slash, okay, as a empty set. Okay, and then in general, we can use this notation to represent a set A. For instance, a set A, which is a collection of elements X, and then this X satisfies certain conditions. So we can use, for instance, so let me just say X satisfy certain condition. Right, so for instance, we can write it as A, and then we can say, let's say X, and then this X is greater than equal to 1, and, okay, X is greater than or equal to 1, and X is less than or equal to 100. Okay, so this is a condition that the elements X satisfied. And sometimes we can use a general notation to indicate it's a certain condition. For instance, we can use a function phi of X. Okay, so that means we can say A is a collection of element X such that phi of X is true. So this is a general way, or is a universal way we write a set. Okay. And then we can look at the following relations. One is a member of, the other one is a subset of. So in this A, of course, we know 2 is a member or an element of A. So we use this notation to indicate it is a member of. And also 1, 2 here is a member of B. And this is an empty set. And it is also a member of C. And now, this empty set, okay, remember this is also an empty, so this is an empty set. This is empty set. Okay, so this empty set is a subset of C. Actually, an empty set is a subset of any set. Okay, because it doesn't contain anything. All right, but for this B, this empty set is not an element of B, although this empty set is a subset of B. Okay, so because empty set is a subset of any set. For A here, of course, a subset of 3. So a set of 3 is a subset of A. And for D, AB, which is a subset, which is a set, is a subset of D. Okay, so this is easy to see. All right, and then we're going to look down here. We are going to define a power set of set X. So assuming X is a set, then P of X, denoted by 2 to the X, is the collection of all subsets of X. Okay, so this S is a subset of X, all of them, put them together. So that, of course, includes, so this 2 to the X will include an empty set and this set X itself. For instance, when A is 1, 2, and 3, then the power set of A, the power set of A can be written as P of A. Okay, so we're gonna look at this set. Of course, the empty set is always in 2 to the A in its power set, the set itself. So we got empty set and the set itself. And then all the subsets. So 1 is a subset, okay? So set of 1, set of 2. So sorry, this is set 1, set 2. So these are all the subsets. Okay, so that is the set notation we're going to use a lot. Okay, and then we are going to define a cardinality of a set X, which is the total number of elements in X, and we're going to use bar X bar to indicate the cardinality. Okay, so the cardinality could be finite and of course could be infinite. Okay, so for instance, in the previous example, the number of elements in A, or the cardinality of A, is 3, and the cardinality of B, which is the Cartesian product of A cross A. Okay, so that is the cardinality of A square, which is 9, and cardinality of C is 4. Likewise, cardinality of D is 4, and the cardinality of the power set of A, 2 to the A, is 2 to the 3, which is equal to 8. Okay, so that's straightforward. And then we are going to look at infinite sets. For infinite sets, we have countably infinite and uncountably infinite sets. Okay, so these, so something that's infinite could either be countably infinite or uncountably infinite. Okay, so for instance, natural numbers, we denote natural numbers by this n, integers denoted by this z, okay, and rational numbers denoted by q are each countably infinite. They are infinite, but they are countably infinite. In other words, all the elements in each of these sets can be enumerated. Okay, you can list them continuously, right? Like x1, x2, xn, blah, 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 right? And then uncountably infinite sets include, for instance, real numbers. Okay, you could denote real numbers by this R, and complex numbers, denote this by C. So they are each uncountably infinite. So now let me ask you a question here so we can think about that, and I'm going to answer this question later. So this is a question with a star sign, so this means a little bit difficult. So it's a 1-star question. So let A be countably infinite. Then we want to know whether 2 to the A, the power set of A, is also countably infinite. Okay, so we're going to answer these questions after we look at proof techniques. Okay. So next we are going to look at the operations on sets, some of the operations on sets. So here we let X and Y be 2 sets. Okay, then the common operations we have is intersection. So this is intersection. It's called intersections. And then we have a union. And we have difference. Okay. So X intersect Y is the set of elements that appear in both sets. Okay, so in this case, 1 appears in X and also appears in Y, so 1's in here. 3 appears in both, and B appears in both, and none of the other elements appears in both. So that's intersection. And this is a union. Union just means that whatever that appears in X or Y will be in the union. Okay, you just put all the elements together. Of course, you don't contain repeated elements. For instance, 1 in X, 1 in Y, so you only put a copy of one copy of 1 in here. And the difference, X, we call it minus, okay? So we say X minus Y would be anything that's in X, but not in Y. So for instance, 1 is in X, but 1 also is also in Y. So 1 is not in the difference. And 2 is in X, and 2 is not in Y. So 2 is in X minus Y. Okay, so similarly for A and C. So for the intersection and the union, we have this, we call it distributions. Okay, so so this is x intersect y union z, then it's equal to x intersect y first, and then union x intersects z. Okay, so these are straightforward. And then we define complement. Okay, then this operation called complement. So, okay, so this is called complement. Or complementation. Let U be the set of all elements we are dealing with. And this U is called a universe. And then let X be a set in this universe. That means X is a subset of U. Then X bar, or the complement of X, is U minus X. Okay, so that is complement. And then we have the De Morgan laws. So X union Y complement is equal to, you take the complement of X first, and Y, the complement of Y, and then make an intersection. And then for the complement of X intersect Y, it is the complement of X union the complement of Y. So this is the Morgan laws. Okay, so next we're going to look at Boolean variables and operations. So let X and Y be two Boolean variables. That means their values are either 0 or 1. And 1 here means true and 0 means false. And then we have X or Y, X and Y, and negation X. Okay, so X or Y is equal to X. So this is denoted, okay, so we should say, also known as X plus Y. So this is the same. So sometimes we use this notation, and sometimes we simply use this notation. And the definition of this is the maximum of X and Y. So that means if X and Y contains a 1, one of them is 1, then it's always 1. If both of them 0, then this is a 0. Okay, and X and Y, sometimes we call this, okay, X, Y. So this is like addition, this is like multiplication. So because, so this is equal to 1 only when both of them are 1. If one of them is 0, it's 0. So that is equal to min of X and Y, or simply like X times Y. Okay, so this is X plus Y modular, I'm sorry, it's just X plus Y. So sometimes we use this notation. The negation will be, negation of X is just 1 minus X. Okay, if X is 1, then it is 0. Otherwise, it is, if X is 0, it is 1. So these are 3 basic. So these are basic. And actually, this is what's needed. Let's just say basic. So from here, we can define other Boolean operations. For instance, this X implies Y, okay, which is simply equal to the negation of X or Y. Okay, so, and then X is equivalent to Y, which is just X implies Y and Y implies X, and X exclusive or Y, which is this XY, sorry, X plus Y modulo 2, which is the negation of X is equivalent to Y. Okay, So as you can see here, these three Boolean operations can be represented by these three basic operations, or and negation. Hence, sometimes we just call them a basic operations because they are sufficient to represent all other Boolean operations. And we also have the Morgan laws. Okay, X or Y negation is negate X and negate Y, and X and Y negation is negate X or negate Y. So sometimes we also write it this way: X or Y negation, put the bar on top, it will be X negation and Y negation. You can also write this as, so this is the same, so this X plus Y negation, that's equal to negation X times negation Y. Okay, so we are going to use this interchangeably. Okay, next we're going to look at sequences and tuples. Okay, when we look at sets, a set is simply a collection of elements, and there is no order. There is no ordering of the elements. If you put an order on these elements, then we're going to call this object a sequence. So a sequence is an ordered collection of elements where an element may appear multiple times, right? For instance, 1, 2, 3, 1. So this 1 appears 2 times. And if you switch the order, they are not the same object. Okay, so 1, 1, 2, 3 is not the same as 1, 2, 3, 1 if this is a sequence. Okay, so a set, okay, so is simply an unordered collection of elements where an element may only appear one time. For instance, if we have this set 1, 2, 3, 1, and it is simply equal to 2, 1, 3, or 1, 2, 3, right? So each element appears only once. In some occasions, we need to look at a different sets, call it multi-sets, also known as a bag of words. So in this bag of words set, or in this multi-set, we allow multiple appearances of the same element. So let's use this brackets to indicate this is a multi-set. So 1, 2, 3, 1. This 1 appears twice. So this is not equal to 1, 2, 3. Okay, but it's not ordered. So you put 1, 1, 2, 3. So this is the same as this. So these are three different objects. Okay, sequence, set, and multi-sets. And then for the sequence, it could be just like sets, it could be finite or infinite. So a finite sequence is called a tuple. Sometimes we also call it a vector. And a k-ary tuple consists of k elements. Well, we can call it k-dimensional vector. For instance, a binary tuple is a 2-ary tuple. Okay, so the binary means or is a two-dimensional vector. Okay, so it's straightforward concept. All right, so next we're going to look at functions. Okay, a function, we usually call it a small, we use a small letter to indicate the function. And then we use capital letters to indicate sets. So this is a mapping, okay? A function is a mapping that maps an element in A to an element in B, okay? But here it says without one-to-many mapping. So that means you cannot map one element in A to multiple elements in B. Okay, so if, for instance, if this is A, maybe start a screen here. Okay, so let's say this is A, this is a set A, and this is a set B. Okay, so a function would be mapping an element. Let's say this is x1, 2. So this is a y1. So this is f. X1 is equal to y1. So x1 is in A and y1 is in B. Okay, so the same function could map multiple elements to the same element. So this would be f of x2 is equal to y1. So this is y1. However, we cannot map a single element into multiple. So this is not a function. This is not a function. But of course, this is legitimate, but this is a legitimate mapping, so we're going to call it relation later. So a function is a subset of relation. Relation contains more. Okay, so in doing so, we can always have for a function. So this is for a function. We always have x is equal to x. Right. So if this is a so the relation here. So the one here is a relation. The relation does not have this. Okay. So that's something we want to make it clear. All right. So now we look at several notations or several notions of some particular functions f. Okay, so f is injective, which is also called one-to-one if it is a one-to-one mapping. So this is the definition. If f of x1 is equal to f of x2, then x1 has to be equal to x2. Okay, so this is a one-to-one mapping. And this is on-to mapping, which means that f is always defined on any elements in A. So that means for all x in A, there is always a y in B such that f of x is equal to y. So in this particular case, sometimes we also call A is a domain. So this A is a domain of f because it's always defined on A. And then f is surjective, and we call it onto. That means that for any y in B, there is always an x in A such that f of x is equal to y. So this is called a range. So this is a range of f. And we called f a bijection. In other words, f is bijective. The other name for this is one-to-one correspondence. If f is total, injective, I'm sorry here, if f is one-to-one, total, injective, and surjective. So let me add this one here. If it is total, I'm sorry, one-to-one, okay, one-to-one, total, injective, and surjective. So when f is a bijection, then we can define its inverse. Okay, so f is invertible if and only if f is bijective. And the inversion is denoted by f to the negative 1. Okay, so it is a mapping from B to A. And then we can define a operation called composition. So let f be a function from A to B, g be a function from B to C, be two functions. Then, okay, so it should be, the composition of these two should be, so this should be G, this should be F. Okay, so that's G circle F is a function from A to C. So I'm going to make a correction on my slides. So which is simply equal to, so this should be or maybe so maybe okay. So we just switch the order. Okay, so this will be F G F G. Okay, so this is a typo. I'm going to fix this typo. Okay, so if F is invertible, then we have F compose F inverse is equal to F inverse compose F, which is the identity function. The identity function means for any x, it just maps x to itself. Okay, so this is a one-to-one mapping. All right, so now we can define what it means by countably infinite sets. Okay, a set is countably infinite if and only if. Okay, so this is a shorthand for if and only if this set is one-to-one correspondent to n. So this is the natural numbers. So in other words, all the elements in a countably infinite set can be enumerated as, right? So can be enumerated as starting as A1, because that corresponds to 1 in this set. And then A2, you look at the index, right? So the index just gives you n. Or if n contains 0, then you can start from A0. Okay, so this is one-to-one correspondence to n, and that is called countably infinite. Now we look at relations. So as we said earlier, a function f can be represented by this set. Okay, well, actually, function we didn't say it earlier, but this function f can be represented by a set. of pairs x, y, such that x is in A and y is equal to f of x, okay? Where if y1 is equal to y2 only when x is equal to, x1 is equal to x2. Okay, so that's function. But if we generalize this to allow one-to-many mapping, then we have a relation. So a binary relation R, okay, which is a subset of A, which is a subset of Cartesian product of A, allows y1 is not equal to y2, even if x1 is equal to x2. And then we can define a relation. Then we say a relation is reflexive if for all x, x and itself is related. And R is symmetric if for all x and y, if x is related to y, then y is related to x. So this is symmetrical relations. And we say R is transitive if you have three elements x and y, x, y, and z, such that x is related to y and y is related to z, then x is related to z. So this is a transitive. So then we say that R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. So here's an example. We can define a relation on the Cartesian product of n such that I is related to j if and only if I is a, so in other words, if and only if I minus j is a multiple of n. In other words, I minus j is equal to 0 modulo n. And this relation can be represented as this, use this notation. Okay, so this is equivalence sub n. Similarly, we can define a, so this is a binary relation, and we can define so we can define a n dimensional relation or NRE relation will simply be a subset of Cartesian product of A. Okay, so that there are n many A's. So that is an NRE relation. So that's an easy generalization. Okay, so next we are going to look at graphs. So we can view a binary relation over a set V as a graph. Okay, so so this graph then consists of two parts. One is V, the other one is E, where V is a set of nodes or vertices, and E is a set of edges on vertices representing they are related. Okay, so where E is a binary relation, is a set of edges, and V here is a set of nodes, and sometimes we call nodes vertices. And we can also call edges arcs. Okay, so people will call this arcs. arcs, okay. All right, then we can define a directed graph. That means that if UV is an edge, but it does not imply VU is an edge. Now remember, this is a tuple, right? So it's ordered pair. If the edge is ordered, it has a direction, then it's called directed graph. So sometimes to have a better visualization, we will say U, so this is an edge, this is a node, and then U to V, we use an arrow to indicate this is directional. So this is V. So I should write a better arrow. Okay, so U to V does not imply V to U. So that's directional. And unidirectional will be without direction, right? So this is U, this is V. So if U is related to V, then of course V is related to U. And then for weighted graph, okay, either directional or unidirectional, we have on the edge itself, we have a number, W, which is well, it does not have to be greater than or equal to 0. Sometimes it could be negative. So let me just remove this. Just a real number. I'm going to fix this on the slides. Okay. So it's just a number. So that indicates the weight. And then we define a path. So a path is a sequence of nodes, V1, V2 up to Vk, such that, okay, so they can be connected. So if it's directional, the direction should always be in the same directions, like this. And if it's not directional, then they don't have to be. So if the directional should always have the same direction. Okay, so let me draw. Let me draw it here. Okay, so this is a path, right? So in this path, the same vertex can appear multiple times. Okay, so but it's still a path. Like you may have, for instance, this number, this one and that. So this one and that one would be the same. So if we don't allow vertices to repeat on the path, then we have a name to it, which is a simple path. So a simple path is a path on which a node can only appear at most once. And similarly, we can define a circuit. A circuit is a path such that the last the last node is the same as the beginning node. So which means that, so this is the same. So which means you form a circuit. Okay, so there's a beginning, And then this is also the last. If it's directional, you have an arrow. If it's unidirectional, you don't have an arrow. So that's called a circuit. And if you don't allow any nodes to repeat except the first and the last node, then it is called a cycle. Okay, so there is a difference between a circuit and a cycle. Cycle just means that you don't have any nodes repeated except the beginning and the last node. And then we can define a tree. A tree is a connected acyclic graph. Okay, a connected graph means that for any two edges, there is always a path connected them. That's called connected. Acyclic graph means this graph has no cycles. Okay, so if it's connected and acyclic, then this graph is called a tree. A tree there must be a node that does not, that can be considered as a root. Okay. All right. So now we look at strings and languages. So we first define, oops. So we first define an alphabet. So an alphabet is a set of symbols. And this alphabet is often finite. It is customary to denote an alphabet by a capital Greek letter, big sigma or big gamma. Okay, so it is a set of symbols, just like the English letters, right? Or like digits, punctuations. So these are symbols. And a string over sigma is a finite sequence of symbols. So it is a sequence. That means the order is an order thing. Okay, it's a finite sequence of symbols, and this finite sequence could have the same symbol appear more than once. Okay, so a language then is a set of strings over an alphabet, which of course could be infinite. The length of a string X, denoted by bar as bar, is the number of symbols it contains. Okay, so if you have to use a, so you can think of it as an ordered sequence, right? So that's a string, and then you count the number of symbols contained in this sequence, and then this is the length. For instance, the alphabet for the English language consists of 26 letters, small case and capital case, 10 digits, right, from 0 to 9, punctuation, right, period, comma, quotation marks, question marks, right, so punctuation, and other symbols such as $sign, pound sign, and space. So you must have a space to segment words. Okay, so a word, then in our case, is simply a string of, in English, a word is a string of letters. A sentence is a string over the alphabet, including space, right? And English is a set of grammatically correct strings over its alphabet. So this is an example of a English language. But of course, in general, for strings and languages, we just simply consider languages as a set of strings over a finite alphabet. Okay, so that's a languages, set of strings. Now let's look at proof techniques. So we're going to use several examples to show these techniques. So this is a proof by construction technique. And we first look at this theorem that says for any even number, right? So this is n is an even number, which of course is equal to 2 times m for some m. So this m does not have to be even. But we want to say this m here has to be greater than 1. So that means this even number has to be at least 4, right? There always exists a 3 regular graph of n nodes. So what is a 3 regular? Which means that every node in this graph has exactly 3 degrees. Okay, it's a 3 degree node, 3 degree graph. So there's a 3 regular graph. So to prove it, we simply do it by construction. So for instance, what we're going to do here is form a cycle first. So we can say n. So this n starts from 0. So let's say 0, 1, 2, up to, let's say, even finally, this is 2m. So this is, and then we just connect them. So this forms a cycle. So 0 to 2 to the m. Oh, so this is not even numbers. This will be 2 to the m minus 1. So let me put 2 to the n minus 1 here. So these are the numbers. Okay, and then let's say this is m here. And what I'm going to do is starts from 0, make a connection to m. 2, let's say this is m plus 1. So eventually we just make another link, okay? So as you can see here, so this construction is doable. Maybe I can use a smaller number. So let me just say m is equal to 3. So we have, in this case, 6 numbers. Okay, so 6 vertices. 1, 2, 3, 4, 5, 6. Let's call it 0, 1, 2, 3, 4, 5. So we make a connection. Connect them. And then this is m. So we got 0 to 3, 1 to 4, and 2 to 5, right? So you look at each node, then you see their degree is exactly 3. So this is a proof by construction. Next, we're going to show a technique called proof by contradiction. So here we're going to say square root of 2 is irrational. Okay, so to prove by contradiction means suppose what you want to prove is not correct and you want to derive a contradiction. So then suppose square root of 2 is rational. That means there are positive integers m and n such that first GCD of m and n is 1, which means that m and n do not have a common divisor greater than 1. If they have, we just reduce them, remove the factor, such that, okay, so for this m and n, we have square root of 2 is equal to m over n. So this is from this assumption. So then we multiply, we squared both sides, we get 2, we put this n squared over, so we get 2 times n squared is equal to m squared. Because this m squared is equal to 2 times an integer, so m squared is a even number, which means m has to be a even number, because m squared is, then m has to be. So that is, there is a positive k such that m is equal to 2k. So replace m squared by, replace m by 2k, so that you get 4k squared. So remove that 2, you get n squared is equal to 2k squared. And again, n squared is an even number. That means n is even. So then GCD m of n now is not equal to 1 because it has a factor. Both of them is even. It has at least a factor of 2. So that contradicts, that is a contradiction. Hence, square root of 2 cannot be rational. The next proof technique is proof by induction. So here we are going to do a very useful summation. So this is called geometric summation. Let R be a number which is not equal to 1. And we want to sum this up. R to the 0 plus R to the 1 plus blah, 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 plus R to the n. And this is equal to R to the n plus 1 minus 1 over R minus 1. Okay, because R is not equal to 1, so this R minus 1 is not equal to 0. So by induction, we have 3 things to do. One is to do the basics, and then we do a hypothesis, and then we do an induction step. So basis will be the left-hand side is R to the 0, which means when n is equal to 0. And the right-hand side is when n is equal to 0, that's R minus 1 over R minus 1, that's 1. So this basis is when n is equal to 0. So both sides are equal. Okay, so the basis is proven, and then we make a hypothesis, which means that for any k greater than or equal to 0, because that's from the basis, and less than or equal to n, the equality holds. So this equality holds. That is, we have this R0 plus R to the 1 plus blah, 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 plus R to the k is equal to R to the k plus 1 minus 1 over R minus 1. Then the induction step is we want to show this equality also holds for k plus 1. Okay, so for k plus 1, you just add one more term here. And then this, so we have this hypothesis for this part, which is equal to this. And plus R to the k plus 1. So you do a simple arithmetic simplification, then you get this. So then, of course, it is also true for k plus 1. All right. Okay, so the next proof technique is proof by equality. So we can sometimes use equality to help us to manipulate some expressions. So in the previous example, we use induction to prove that R0 plus R to the 1 plus blah, 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 plus R to the n is equal to R to the n plus 1 minus 1 over R minus 1. So now that equality can also be derived using this technique. So it is actually a construction technique. So to do so, we simply let S be the summation. S is what we want to find by getting rid of this dot, dot, dot notation. We want a closed form. Think of this as not closed because it has these things in here. So we let it be S. S is what we want to find. And then we multiply S, this equality. Now this is equality. We multiply S by R and the right-hand side by R. They are still equal. So that means RS is equal to R to the 1 plus R to the 2 up to this. Okay, and then we put an R0 in it. Because you add R0, then you got to subtract an R0. So this equality still holds. And after you put an R0, you add R0, and then you can take this R0 up to Rn, and then this R to the n plus 1 minus R0. So we get this is equal to S, right? So this is equal to S. So this Rs is equal to S plus R to the n plus 1 minus R0. You move S over, you move R plus 1 down, then you get this, right? So this is a technique, a very useful technique. All right. Oh. Okay, so let me give you another example because that's also useful. Is how do you add 1 plus 2 up to n? So using this technique, we can just let S be 1 plus 2 plus n. So this S is what we want to find. And then because the summation you can have, so this is still the same. So it's n plus n minus 1 plus 1. So you add them up. So at the left-hand side, you have 2s. And then at the right-hand side, right, so you look at each of these columns. Each column is equal to n plus 1, and you have n columns. So that means 2s is equal to n times n plus 1. Hence, S is equal to n times n plus 1 over 2. Right, so this is a very useful, so I would like you to remember this technique. The next technique is a proof by manipulation. So we want to show the summation of 1 over k times k plus 1 for k from 1 to infinity is equal to 1. Okay, so the manipulation will be just manipulate this number, so which becomes 1 over k minus 1 over k plus 1, because so for k to 1 up to n, so you can think of this, for instance, 1 over k times k plus 1 is just 1 over k minus 1 over k plus 1. So you add them up, k from 1, let's say, to n, then you get the intermediate parts cancel. For instance, you look at the next term from k. So the next term will be, so this is current term, the next term will be k 1 over k plus 1 minus 1 over k plus 2. So these two cancel. So ultimately, you have the beginning term and the last term. The last term is minus. The beginning term in this case is 1. The last term is 1 over n plus 1. So when n goes to infinity, this goes to 0. Hence, you get 1. All right. So now finally, we are going to look at a proof technique by combining some of these techniques and answer our questions Q1. So what we want to show now is that if A is countably infinite, then its power set 2 to the A is uncountably infinite. Okay, so the proof is like this. So first, we assume that this is the assumption. The A is countably infinite by definition. That means the elements of A can be enumerated because it is one-to-one correspondent to n, to natural numbers. So these index are natural numbers. Okay, so now we are going to use two techniques. One is, two techniques, proof by contradiction and proof by construction. So we assume, on the contrary, that 2 to the A is countably infinite. So this is a proof by contradiction. Okay, and then we are going to construct something that violates this assumption. Okay, so violates this assumption. Because 2 to the A is countably infinite, that means that its elements, again, they are sets, right, can be enumerated as A1, A2, up to AN, now as capitals. Now, we're going to construct a new subset S of A as follows. So we look at each integer I. We're going to look at AI. We're going to put AI in S, if and only if AI is not in capital AI. Okay, because for each AI could either be in this set or not. If it's in this set, we're not going to put it in S. If it's not in this set, we're going to put this in S. So then, of course, S is a set. Okay, S is a set. Hence, S is an element. Now, S is a subset of A because it only includes these elements in A. So it's a subset of A. So S is an element of this power set of A, because this gives you all the enumeration, gives all the sets in 2 to the A. So that means that this S has to be one of them. That means there is a K such that S is equal to AK. So now for this K, if AK is in small ak is in capital AK, that means that because S is equal to AK, that means is equal to A. It means that AK is in S. But then we know by construction of S AK is in S if and only if AK is not in capital AK. And you look at this two, that's a contradiction. So the contradiction means that you assume that 2 to the A is countably infinite is wrong. Okay, that assumption is wrong, and hence it proves that 2 to the A is uncountably infinite.